we go to some quota methods and paradoxes from quota method. There are two methods that we are going to discuss, namely the Hamilton method and the Lowness method. Both methods satisfy the quota rule. So in the next slide, to further explain this method, we are going to look into a situation where there are three states are going to conduct a conference with only 100 seats. So to properly appropriate the number of seats for each states, we are going to use the Hamilton method and the Lowness method. So at the left table, we use the Hamilton method, and the right table applies the Lowness method. So at the first row, we can identify the total population, which is equivalent to 1 million. And then the standard quota is shown at the next row, and its usual round off on the third row. And then we have the lower quota. So basically, bakit natin kinuha yung lower quota? Because as we can see, sa usual round off, yung total number of seats ay 101, which exceeded the number of seats na kailangan natin, which is 100 lang. So kukunin natin yung lower quota na nagtotal sa 98. So, since 98 lang yun, kulang ng dalawa, we have to identify which state is going to take the surplus seats. For Hamilton method, ginamit niya ang absolute fraction part, while Lowness method uses the relative fraction part. So basically, when we say absolute fraction part, it is only the fraction part of the standard quota. For example, for state A, yung standard quota niya is 65.7. So yung fraction part niya is 0.7. And sa Lowness method naman, yung relative fraction part, makukuha yun by dividing the fraction part by the integer part. So dito ulit sa state A, kita natin, for example, 0.7 is divided by 65 rather. So, ayan, nakuha natin yung 0.01. To allocate which state will take the surplus seat, titingnan natin kung ano yung mas malaki. And sa Hamilton method, nakita natin na states A and B took the surplus seats, while states B and C took the surplus seats for Lowness method. So, both are quota methods. Next, we are going to discuss about the paradox, wherein it is just the contradictory statement na pwedeng maging true since it is based on a valid deduction from acceptable premises. So, papasadahan lang natin itong types of paradoxes na meron tayo, namely the population paradox, the Alabama paradox, and the New State paradox. So, when we say population paradox, it basically means na merong increase sa population ng state, kaya mababawasan yung seat allocation niya. Yun yung paniniwala sa population paradox. While Alabama paradox believes that if the total number of seats increases, merong isang state na mababawasan yung seat allocation niya. While New State paradox, on the other hand, means that adding a new state with its fair share of seats can affect the number of seats due to other states.
As we saw in the previous parts of the video, standard divisor and standard quota are mostly used in apportionment schemes. However, there are times when modified divisors are used instead. Modified divisor is obtained by trial and error and is used to get the modified quota. To obtain the modified quota, we divide the state population with the modified divisor. This type of apportionment is called divisor methods. There are three types of divisor methods. The first one is Jefferson method, which is attributed to Thomas Jefferson and was used from 1731 to 1830. Let us have an example. 10 seats should be allocated to a population of 1,100 consisting of 3 cities. City A has 696 people, B 268, and C 136. First, we get the modified divisor. Modified divisor is calculated using the formula population over number of seats. Using the values in our problem, we obtain 110. Now that we have our first modified divisor, we assign seats using these steps. Step 1. Calculating the standard quota. We can remember that the formula for standard quota is number of seats multiplied by state population over total population. Using this, we obtain the following answers. Step 2 is assigning the lower quota. Remember that in obtaining the lower quota, we simply round down each standard quota in the nearest whole number. We have 6, 2, and 1. Step 3. If there are surplus in seats, modify the divisor so that when each state's modified quota is rounded down, no surplus seats remain. But since in our problem there is a surplus in seats, adjust the divisor, which is 110, to 98. Step 4 is just repeating step 1 and 2 but with the new modified divisor. The new lower quotas obtained are 7, 2, and 1. Adding them all together, we get 10. The second divisor method is Adams' method. It is from John Quincy Adams but was never used by the Congress. It is very similar to Jefferson's method but uses a modified divisor larger than the standard divisor, which in turn produces smaller modified quotas that are rounded up. Consider the situation in our previous problem. To get the allotment for each city, we follow these steps. Step 1. Assigning upper quotas. You can remember that the standard quotas obtained are 6.33, 2.44, and 1.24. Rounding them up, we get 7, 3, and 2. But since these numbers give 12 seats, we modify the divisor to get smaller allocations. We choose a larger divisor than 110, say 135. Step 3 is assigning upper quotas using the new modified divisor. We get 6, 2, and 2. We get a total of 10 seats. The third and last divisor method is Webster's method, which is devised by Daniel Webster and was used in the 1840, 1910, and 1930 apportionments. Using the same problem, we are going to allot seats using these steps. 1 is rounding off the standard quotas in the usual way. We get 6, 2, and 1. Since this only results to 9 seats, we modify the divisor, say 107.2 to get larger allocations. Step 3 is once again calculating for the modified quota but using the new modified divisor. Remember that we should round them up in the usual way. So we get 6, 3, and 1, a total of 10 seats. This table shows the comparison of allotments decided using different methods. We see that after using the 3 divisor methods, we obtain 3 different apportionments. In Jefferson's method, City A is allotted 7 seats, B has 2 seats, and C has 1. In Adams' method, 6 seats is given to A, 2 to B, and C has 2. In Webster's method, A has 6 seats, B has 3, and C has 1. It is known that the 3 divisor methods can violate the quota rule. However, it can be proven that none of the 3 divisor methods can suffer from paradoxes. So the real question now is, which is better, quota method or divisor method? Mathematicians Michael Belinsky and H. Peyton Young tested this and obtained a result that says no apportionment is mathematically flawless. It is reflected in the table on your screens. According to Belinsky and Young, any apportionment method that does not violate the quota rule must produce paradoxes, and any apportionment method that does not produce paradoxes must violate the quota rule. Additional divisor method was proposed by Joseph Hill and Edward Huntington in 1911 and was adopted by the U.S. Congress in 1941. It is the method of equal proportions and is similar to Webster's method, but rounding off depends on the geometric mean. At the geometric mean, we obtain the modified quota, and if modified quota is between integers n and n plus 1, then the geometric mean would be the square root of the product of n and n plus 1. If the modified quota is less than or equal to the geometric mean, then the modified quota is rounded down. The modified quota is larger than the geometric mean, then it is rounded out. A fun fact, the first U.S. presidential veto was a math bill. In 1791, President George Washington vetoed Hamilton's bill on apportionment. Jefferson's method was adopted instead.